We breathe oxygen every day, and we don't have to think much about it because actually all the plants around us and the algae in the ocean happily produce it for us. In my field of research, we are interested in how this actually came about. How did we reach this lucky situation for us? When Earth formed, it was a harsh and reduced environment, and oxygen only slowly started to increase, actually in a kind of two-step process. About 2.3 billion years ago, oxygen started to rise. Then another 1 billion years, it actually stayed at really low levels. And only about 0.4 billion years, it was sufficiently high to allow higher life to flourish, like us or dinosaurs. So the big question is, how was this pattern shaped? Which processes might have actually initiated this first major rise, and which ones might have tempered it afterwards? It must have been either geological or volcanic processes or microbial processes, because Earth was microbial for most of its history, and organisms like us only evolved much later. It is also very clear that the main driver was the process of oxygenic photosynthesis, the only significant source of oxygen even today. It evolved in the form of cyanobacteria, maybe already 3 billion years ago. So after the evolution, it still took quite a while before oxygen could rise. So what might have been the mechanisms that actually delayed oxygenation that much, and that delayed also the evolution of organisms like us? In this study, we are trying to throw another idea into possible factors that might have affected this oxygenation pattern. And this is Earth's rotation rate. Earth's rotation rate equals actually day length. The faster Earth spins, the shorter the day is. And it might have been as short as a couple of hours when the Earth-Moon system formed about 4.5 billion years ago after the Big Theia collision. Ever since, day length is increasing, and only recently we have reached our 24-hour day. So we are interested in understanding whether there is actually a link between Earth's oxygenation and the change in Earth's rotation rate. This link is not obvious, and we're trying to find it in the form of microbially built structures that are called microbial mats. And these might have been actually the hotspot of evolution of many microbial metabolisms, such as oxygenic photosynthesis. So we tried to specifically look for the effect of day length on oxygen release from these microbially built structures. To understand more about the potential link between day length and oxygen release from microbial mats, we first simulated their response with modeling, and then we moved into validating our potential insights in natural systems. And finally, we went into some upscaling of our insights and integrated the results in a global box model. So the first step was this dial numerical simulation of microbial mat processes. We started very simple with just integrating cyanobacteria and maybe some respiratory processes to see how much oxygen would be released dependent on day length. And then we slowly made it more and more complex. The main outcome of this would be the response of oxygen release and potentially of net productivity to day length. Our insights then had to be validated in some real system. And for that, we went to the Middle Island Sinkhole, which is located underneath the Lake Huron water column. It's a very pristine environment that is characterized by low oxygen in the water column above cyanobacterial mats. So we took these mats, we sampled them, and then we exposed them to varying day lengths and measured the oxygen release from these systems continuously using a very nice tool called microsensors. From all of that, we started to get an understanding of how and why microbial mat oxygen release would respond to day length. Based on the first two steps, we gained understanding of how dial dynamics would imprint in the form of net productivity of systems. And this is a really important factor, actually interacting with atmospheric oxygen concentration on the long run. So we took our results and integrated them into a global box model of atmospheric oxygen and tested if day length could have an effect on the long and large scale. Coming back to our initial questions, is there actually a relation between day length and oxygen release from microbial mats? We actually found the answer yes. It is a fundamental mechanism. And the second one, would it have actually mattered? And our answer was finally also maybe yes. So at the basis of our hypothesis was the idea that any kind of gross production of oxygen by cyanobacteria should actually not be affected by day length. If you imagine a mixed photosynthetic system and just increased light faster and slower, which would happen with increasing or decreasing day length, we would not expect any change in gross production. But as soon as the cyanobacteria would sit in a laminated microbial structure, oxygen release from this structure will be additionally governed by the physics of diffusion. And this link between microbial processes in these mats combined with mass transfer limitation by diffusional limitation and changes in day length might be the link actually between rotation rate and Earth's oxygenation pattern. First, we did find consistently that microbial mats exported more oxygen the longer the day was. We found that in all mathematical simulations, and it actually became more and more prominent with more and more metabolic complexity. This was most pronounced actually in our environmental example where we tried to validate our hypothesis. There, the dependency of oxygen export was steepest dependent on day length. So this was one really important step forward. We realized that whatever we do, whatever metabolic processes we integrate into our simulations, there will always be more oxygen export and thus also more net productivity in benthic microbial systems, the closer we move to a modern 24-hour day. The second big question then, as mentioned before, would it have mattered? This is a really difficult question. We have established that there is a fundamental mechanism that definitely changes net production with day length. This net production could relate to burial, which is a long-term factor affecting Earth's oxygenation state. So if we assume now that there is a direct link between the two, and if we also assume that the world was indeed a mat world with microbial mats covering Earth's coasts, if we make all of these assumptions, it is well possible that Earth's rotation rate, so a planetary mechanism actually, might have caused major increases in Earth's oxygen levels and might have even contributed at least to driving it beyond thresholds that allowed higher life to flourish. The drivers behind Earth's oxygenation remain mysterious. There are many ideas around how Earth's oxygenation pattern might have come about from all kinds of different disciplines. So with this study, we throw a new idea into the pot of clever ideas around the driving factors between Earth's oxygenation. It remains highly speculative. We try to validate it as much as possible. But there remain many uncertainties, and that's okay. I think it's very important to come up with different and creative ideas to understand how our planet became what it is today. Unfortunately, we can't travel back in time. So what we can do is try to constrain what made our planet the habitable planet that we have today. And that's not only important for us to understand where we came from, but it's also an intriguing question when thinking about habitability of other planets, right? What do we know about constraints of life? I think we can learn the best from our own history on our planet. What I liked the most about this study was that we were able to work across so many disciplines of science and across so many temporal and spatial scales. It's really nice to think about how microbes and their microenvironment can be affected by changes in the Earth-Moon system, and how this in terms could have affected actually the atmospheric oxidation state of the Earth. This is kind of mind-boggling, and it also emphasizes how important it is to actually work across different temporal and spatial scales in how they interact with each other. I realized during the study how little is actually known about how processes in microbial mats would imprint in the geological record. And this is actually the weakest spot also of our study, is that we don't know how diel dynamics, dial oxygen release, and net productivity would actually link to long-term burial of organic carbon, which is the ultimate determinant of oxygen in the atmosphere. I think this is really important to look deeper into that, to study modern microbial mats that are as old as possible, which is actually kind of hard to find, and to understand how activity in these mats would imprint in the form of signatures, isotopic signatures, biomarkers, etc., etc. Only that will actually allow to more quantitatively assess the effects that we have seen, and eventually also a series of other important effects that microbial mat activity might have had over Earth's history.